Okay, so we're talking about electric potential and electric field. Um, as we talked about potential energy, gravitational potential energy, we have a similar concept that we're going to talk about here with electric potential energy. And that potential you can think of as the potential to do work. That's one way we could think of gravitational potential energy. If I drop a rock off the side of a building, that rock, its gravitational potential energy turns into kinetic energy as it falls, and then that kinetic energy could reveal itself in work being done as it drives a stake into the ground or something, somehow that I wanted it to do some work. So we have a similar thought here. So here's, I guess we're dropping a basketball, and we're dropping a basketball from an initial height to a new height, and the difference in gravitational potential energy is work that is being done here on the basketball by gravity. So similarly, if we took our positive test charge from the last chapter and placed it inside an electric field instead of a gravitational field, because that's what we're experiencing here on the surface of the Earth, is a gravitational field where the further I get away from ground and go up in the air, the greater the gravitational potential energy is acting on me. So I'm going in an increasing gravitational field. Here, if we align our parallel plate capacitor in a similar way, with positive on one side and negative on the other, this negative could be negative charges, or it could be ground, electric ground we would call it. On the positive side, that's an area of high electric potential energy, high electric field strength. Now, this works for our positive test charge, remember? So this Q sub naught is a positive test charge that would be repelled from the positive side and attracted to the negative side. So the change in energy as it goes from the positive region to a more negative region is a decrease in energy, which is work that is being done on the charge by the field. So you can see the analogy here between gravitational field and electric field. Now, this work is the change in electric potential energy. It's a decrease in electric potential energy for a positive charge to move from a region of positive charges, high electric potential energy, to a region of low electric potential energy, negative charge, or zero ground charge. Now, the electric potential energy, the potential energy per unit charge, is called the electric potential. So there's electric potential energy, that's a specific amount of energy in joules, versus the electric potential, which we could then calibrate for whatever amount of charge we have. So work, change in energy per unit charge. So this would be joules per coulomb of charge. So this joules per coulomb of charge is our electric potential. The unit for that is volts. Volts is joules per coulomb. So you've heard of volts. You've handled a 1.5 volt battery or a 9 volt battery, or you know that you plug something into the wall and there's 120 volts. That's what a volt is. And it's tied into the amount of energy that is given to charges inside that electric field. Now, it will depend, it will vary greatly if you are subject to electric charges running through your body out of a 1.5 volt battery. Those charges don't have a tremendous amount of energy, just 1.5 volts. If you run a lot of charges, it might zap you a little bit. But if you plug something into the 120 volt outlet in your wall and got electrocuted by that, that's a huge jump in energy. That's 120 volts, and you can get higher and higher still. So electric potential, joules per coulomb, the unit is volts. The work done by the electric force as a test charge, so we're giving this test charge a value, 2 times 10 to the negative 6 coulombs. Again, it's a positive test charge. As it moves from A to B in this figure, is 5 times 10 to the negative 5th joules. So find the difference in electric potential energy between these points. So we have the work, we have the value of the charge, so the change in electric potential is work divided by the charge. So the change in electric potential energy, the work is negative 5 times 10 to the negative 5th joules. The work that is done, it's going from a region of high energy to lower energy, so it's negative work. It's just as though I took a giant mass and I lowered it down. It has decreasing potential energy. If I lower a mass down, we have decreasing electric potential energy as work is being done on the charge here. So the potential difference, the change in electric potential, is work divided by the charge, so it's a negative 25 volt. It's a 25 volt decrease in electric potential. Now, here's something that we should know with mass, with matter and the gravitational field. If I lift a mass up, I've given it an increase in gravitational potential energy. If I take that mass and I lower it down, it has a decrease in gravitational potential energy. Matter, mass, is always positive. There's no such thing as negative mass. Maybe if we wanted to get into the realm of antimatter, but not even that. So set that aside for a moment, because we know with electric charges, we have protons that have positive charges and electrons that have negative charges. So if I stuck an electron in this same situation, the electron would be repelled from the negative plate and attracted to the positive plate. So it would be just the opposite in how it reacted in this situation. So unlike mass and matter, electric charges can be either positive or negative and will behave differently in how we've defined what a high potential is and low potential. We say that high potential is positive, low potential is negative, but an electron will tend toward the high potential region because that's positive. So electrons behave differently than protons, and it's the opposite of the way that we would think of mass and matter behaving. So protons behave the way that mass would behave in a gravitational field. Electrons do just the opposite. So a positive charge accelerates from a region of high electric potential to low, but a negative charge would accelerate from a region of low potential toward a region of high potential, just because we've defined it that way. It's just a choice we've made. It's actually a choice that Ben Franklin made, if you want to know the truth, because Benjamin Franklin was the one who decided to call electrons negative and protons positive. Really and truly, there's no inherently positive or negative thing about either. It was just a definition that he gave them, and it turns out it's a little inconvenient because we're talking about a proton moving from high potential to low potential, but that doesn't actually happen in matter, right? It's only the electrons that are moving around. So it would be so much more convenient if we did this defined all by way of these positive electrons that are moving from high potential to low potential. Like everything would make a lot more sense, but we're stuck with this way of doing it, and it's all Ben Franklin's fault. So we'll deal with that. All right, so Remember when we talked about conservation of energy and the total energy involved, and at some simple point in time, the only energy that we talked about was kinetic energy and gravitational potential energy, and we have maybe a roller coaster, and it went from a region of high gravitational potential energy, and then it rolled downhill, and that gravitational potential energy turned into kinetic energy, and we could say the total energy of the system was constant. And then we said, well, you know what, if you're rolling a ball down the hill, then some of that gravitational potential energy will reveal itself in the form of rotational kinetic energy, 1/2 I moment of inertia times omega, the angular velocity squared. And so we could do some neat calculations with that. And then we said, well, you know what, you could go one step further, and this ball could roll down a hill, rolling down the hill, but then it could hit a spring at the end, and we have elastic potential energy at the bottom. And if the ball rolled into a spring and then bounced back up the hill, then we'd have 1/2 kx squared for the work that is done by the spring, storing that energy and restoring that energy to the system. Well, now, just in this basket of energies, we now have electric potential energy as another energy. These are all in joules, another type of energy that's part of this conservation of energy realm. Now, in terms of energy, there's one thing that you should know, is that there's a term called an electron volt. An electron volt is the magnitude of the amount by which the potential energy of an electron changes when that electron moves through a potential difference of 1 volt. So 1 volt is 1 joule per coulomb. So if we had 1 electron, which is 1.6 times 10 to the negative 19th coulombs, then an electron volt is 1.6 times 10 to the negative 19th volts. Just a unit for energy that is sometimes used. All right, conservation of energy. Particle has a mass and a charge, and it's released from point A and accelerates horizontally to point B. The only force acting on the particle is the electric force, and the electric potential at A is 25 volts greater than at C. What is the speed of the particle at point B? The same particle had a negative charge, and what would its speed be at point A? All right, so we're conserving energy here. Kinetic energy plus electric potential energy. So when we do that, we'll say, all right, kinetic energy, 1/2 mv squared, equals the change in electric potential. So the velocity is the square root of q times delta v divided by mass times 2 times q. So VB equals the square root of 2q times the change in electric potential. That was 25 volts. I don't know what each value is specifically, but I know that the change is 25 volts. Divided by the mass of this particle. They'd have to give it to us, or if I told you on the homework or a quiz or exam that we're talking about an electron or a proton, you could look up those mass values. And we would get that this particle moving in this field would get to a velocity of 9.1 meters per second. Likewise, if it was a negatively charged particle moving the other way through the same potential, it would also be 9.1 meters per second. Just pointing out the fact that a negative charge behaves exactly the opposite of a positive charge in an electric field. Now, if we want to talk about the potential of a point charge, kind of like the actual voltage of a specific point charge somewhere in space, we'd be taking our Coulomb's law. Remember, the force equals k q1 q2 divided by r squared. But now we're just doing it from the perspective of one thing. So the potential of a point charge that it is exerting in the space around it is kq over r. And then if I stuck another charge in there, then I'd be able to look at what's going on with that one. But this is the potential due to just a point charge sitting somewhere in space, and I can map out a region around it and talk about that potential. So when we do that, and this is less used in our realm of physics, but if you went into electrical engineering, you'd want to have at least have heard these terms so that you're able to fill in whatever deficiencies you have. We're able to define what is called an equipotential surface, and that equipotential surface is a region, distance r, around point charge q, that would have this amount of electric potential, and it would go all the way around in a circle around it. So distance r, radius r, all the way around. So this would be one equipotential surface, and if we jumped out another amount, we'd have another equipotential surface. And theoretically, you could have infinite numbers of equipotential surfaces, but we'll pick some distinct separated values. And so here's superimposed. We have two charges, a positive charge and a negative charge. We have electric field lines drawn in like we had in the previous chapter, but also we're mapping out these regions in space around the charges with equipotential surfaces. If you ever go hiking and climb mountains, you might see something that looks similar to this, where we're noting that we have a huge change in here electric potential energy. In terms of hiking, maybe it would be gravitational potential energy. And you'd say, okay, so I can hike from the top of the mountain to the valley below. And if I do that here, I'm going to have a steep cliff. I'm going to plummet down to the valley below. Whereas if I go this way, I have these equipotential surfaces that are separated a little bit more, and I can go down a little more slowly and then hike around and then go down into the valley below without falling and dying. These equipotential surfaces come into play with capacitors. So capacitors are a physical device that you can hold in your hand, and what it does is it will separate charges from one plate to the other, and between these plates we'll have a region of equipotential surfaces. And that electric field that we defined as newtons per coulomb before can also be represented as the change in electric potential divided by the separation distance. Now this will come into play when we want to talk about designing a capacitor and filling it with some dielectric material, some material that will allow us to separate the charges without the charges jumping across when we don't want them to. A capacitor can store charge for us for release at some given moment in the future. So if I take 1.5 volt batteries and I stick them in a camera flash, if I just ran the 1.5 volts through a light bulb, it wouldn't glow very bright. But if I have a capacitor as part of that circuit, I can extract charge from my battery, and when you turn on a camera flash, if you've ever held one that's not your cell phone, if you've ever turned on a camera flash, you hear whee! That's the capacitor charging up, separating charges from the two poles of the battery, and then when you press the button, it releases all of that charge to travel at once, which when it flows through the camera flash light bulb makes it glow very bright for just an instant in time. So the relationship between charge and potential difference for a capacitor, Q, this is our charge, equals capital C. Now this is capital C as an algebraic quantity, as an algebraic representation in an equation. Remember that if we had n in an equation, it might mean one thing, the number of particles, versus n as a unit is newtons. So there's different examples of that. If we have lowercase m in an equation, We might be talking about mass, whereas if we have lowercase m as a unit, we're talking about distance in meters. So this is such a case where capital C is our capacitance now. It's the capacitance proportionality constant. Capacitance is coulombs per volt. It's how much charge in coulombs you're going to charge in your capacitor, store in your capacitor per volt that you have connected to it. So if I take a 1.5 volt battery and I have a certain capacitance capacitor, there's a certain amount of charge that I'll be able to store in that situation. Now, if we were going to design capacitors, we'd be worried about this dielectric constant that we put in place between the two plates of the capacitor. We're not going to design capacitors ourselves. What we want to talk about then is in a capacitor, how much energy can you store? So the energy that you can store in a capacitor is 1/2 C, the capacitance of a capacitor in farads, times the voltage of the battery that you have connected squared. That's how much energy can be stored in a capacitor and accessed for some time in the future. So it looks like we have a young Barack Obama working here to, doesn't he kind of look? Working to revive this person. We have a capacitor in this device. We're going to jumpstart his heart going again. And the amount of charge that can be stored here. So charge, they're going to charge it up, and then they're going to release it all at once to try to jumpstart his heart, is the E equals 1/2 CV squared. We have all sorts of biomedical applications of electric potential differences. Cell walls will have sodium channels and potassium channels based on getting these particles across the positive layer into the negative layer. So there's all sorts of applications of electric potential, many of which I don't understand. Maybe all of which I don't understand. If you measure your heart rhythm, so your heart is actually beating because of being triggered by electrical impulses. That's why when you get electrocuted, that can be bad. All right, so we have charges in coulombs. We have electric potential in volts. We're going to start putting those together in the next chapter. But I think you have what you need to do chapter 19 homework. So good job.